So, good afternoon, everyone. Today, I, Mayukh Biswas, present before you the work we have done along with Rakshit, Amit, Swain, and Chirabrata Bhaumik at TCS Research Lab, Kolkata. So, the work is on selection criteria of sensor for online non-contact vibrometry of grinding mills. Oh, yeah, sure. Thanks. So if we consider the entire mineral processing circuit, starting from blasting of ores to crushing, grinding, separation, followed by beneficiation, around 30% of energy is consumed in the grinding process itself. Now, this grinding process is carried out using an enormous cylindrical rotating structure called ball mill, wherein the chunks of ore gets crushed into smaller particles with the help of metal balls, which gets impacted with them as the ball mill rolls. Now, what happens is that a few of these metal balls hit the liner of the ball mill, which causes the liner to wear out over time. Now, this is a big problem. You may ask why. So as the liner gets worn out, the grinder efficiency starts to reduce, which increases the power consumption of the milling process. So what do we have to do? We have to replace the liner. The current replacement strategy is based on human intuition. Now, if the human predicts the time to replace the liner in a wrong way, then there will be unnecessary downtime of the ball mill, which will result in a huge financial loss to the company. So, liner health monitoring is the call of the hour. A recent study by ABB has suggested that the vibrational amplitude captured at the shell of the ball mill using an accelerometer captures the liner health of the ball mill. So using this, we can predict the right time to replace the liner and save the unnecessary loss. But here comes a catch. These contact-based sensors, if attached to the ball mill, it can affect the warranty of the structure. And moreover, the maintenance and replacement of these sensors will again lead to downtime, causing loss to the company. So we require non-contact sensing. Now, there are a few non-contact sensors in the market, but we have to consider factors like geometry of the structure, the cost of the sensor, and most importantly, the diagnostic sensitivity of the sensor in question. Till date, no study has been done to quantify the diagnostic sensitivity of the sensor. So we need a method for sensor selection. So this study bridges the gap between the known and the unknown by performing one-time sensor selection study using an accelerometer, and then we later validate our findings using the sensors available to us. So this is the experimental setup. We have used two different ball mills with different geometry, different build material, different balls which have been dropped from above, and different capacity. So in this experiment, we have dropped balls from the opening of the ball mill of different sizes. And we have also attached the accelerometer diametrically opposite to the opening so that the ball falls exactly above the accelerometer. So as you can see, we have used three non-contact sensors for validation. The first one is a 24 gigahertz radar, Innocenti IPS 354. The second one is a 60 gigahertz radar, Econier A121. And the third one is Riftec RF603 LD sensor. So let's move on to the methodology. First and foremost, we capture the acceleration data. So you can see the time series on the right side. If you see the red plot, you will find that there is a DC offset of 9.8, which is basically the acceleration due to gravity, which has to be removed. So after removing it, we know from our prior knowledge of kinematics that upon double integration of acceleration, we get the displacement, right? So there we go. We solved the problem. Or did we? If you see the red plots, it suggests that the velocity and the displacement after dropping the ball is non-zero, which basically implies that the shell will start moving by itself, which is physically not possible. So there must be some problem with our way of working. Well, it turns out that if we see the Fourier transform of the accelerometer signal, there are some components at low frequency which results in accumulation of the DC component. So we need to filter out only that part of this signal which actually contributes the oscillatory part of the motion, which is basically vibration. So therefore we pick two frequencies, FL and FH. So below 30 hertz, we had observed for many trials that there was this there was this noise component, and above 400 hertz, there was also presence of noise. So this part was of our interest. Now, what should be the limits of integration? Well, we should integrate only the part which contains the impact. So for that, we did a joint time frequency plot of the impacts for different ball sizes from the accelerometer signal. So you can see that we chopped off the portion where the impact actually happens. So this becomes our T1 and this becomes our T2. So as you can see on the left side, this flow chart, we have covered up everything and we finally get the displacement. So we sampled the peak displacement for different ball sizes and we get this displacement versus ball size characteristic. We have fit a curve over here. So this becomes our one-time sensor selection study using an accelerometer. Now we validate our study with the off-the-shelf sensors. First of all, we check the resolution of the sensor. So for S1, it is 600 microns. For S2, it is 250. For S3, it is 1 micrometer. So if we check the first sensor, which is the 24 gigahertz radar, and compare it with the vibration displacement characteristic plot, you can see the resolution is twice more than the maximum value which is obtained in this characteristic. And that's why if you can see our experimental results for the displacement obtained from this radar, nothing is seen over here. So we dropped the ball, but this couldn't capture anything. So this goes hand in hand. So if you check for the second radar, the 60 gigahertz two-channel radar, you see that only for the largest ball size, we have detected some displacement. If you check the resolution, it is 250 micron and the largest displacement was 300 microns. And finally, the LD sensor, which has a resolution of just 1 micrometer, it basically showed all the displacements. So the point of this is that suppose your application requires ball size of greater than 4 centimeter. So instead of buying an expensive sensor, you can buy S2. So this will save your budget. So to wrap up, we have devised a methodology to test the diagnostic sensitivity of sensor by performing a one-type sensor selection study. We have captured the vibration displacement of mill shell, and it has been characterized with varying dimensions of ball mill and ball sizes. And yeah, we have also validated our result with off-the-shelf sensors. And in future work, we should vary more parameters to get a better idea of the system. Thank you, and please visit our sensing lab at IIT Kharagpur Research Park, Kolkata.